All right, so we want to find the interval of convergence of the power series. So note that when you want to find the interval of convergence, you basically look like you're applying the ratio test. And if you remember with the ratio test, it states that you need to basically compute a limit. The limit as n approaches infinity of the absolute value of an plus 1 over an. And what you know is that this limit must always be what? By the ratio test. If it has to converge, it has to be less than. It has to be less than 1. Okay. Now, your an in this problem, right? An is just simply 3x to the n over n plus 2 factorial. Now, if I want to figure out what's an plus 1, wherever I see an n, I attach a plus 1 to it. So you're going to get 3x to the n plus 1 over n plus 1 plus 2 factorial, which is just simply n plus 3 factorial. So you have 3 times x to the power of n plus 1 over n plus 3 factorial. All right, so let's compute our limit. So I'm going to show you guys how I do this limit a little differently. So we know that our limit says that we have limit n approaches infinity of the absolute value. Inside of the absolute value, I put the an plus 1 first. So that's 3x to the power of n plus 1 over n plus 3 factorial divided by the original sequence, 3x to the n over n plus 2 factorial. Now, there's a couple of rewrites that I can do here. First of all, when I have x raised to the power of n plus 1, right, so just note, x to the power of n plus 1 is the same thing as saying x to the n times x, right? Or you could say x times x to the n. Because if you look at the x to the n times x, that's just the product rule for exponents, or say that if you multiply with the same base, you can add your exponent. So we're going backwards essentially. If you have x to the power of n plus 1, your base is x, and your two exponents are going to be n and 1 respectively. All right. Another thing to note is that when you look at n plus 3 factorial, if you want to simplify this just a little tad bit, you first have n plus 3 as the first term. The next term is always going to be 1 less than the previous. So if my first term is n plus 3, what will be my next term? N plus 2. So I'm going to leave it as n plus 2 factorial. So the reason why I made these notes on the side here is ultimately I want to simplify what's inside of this absolute values. So first, I would have to change the division to multiplication and then flip it, flip the second fraction. So we'll have 3x to the n times x divided by n plus 3 times n plus 2 factorial times, take the flip, you have n plus 2 factorial now on top and 3x to the n on the bottom. Now, I think this will simplify nicely because x to the n, 3x to the n will cancel. N plus 2 factorials should cancel. So what we'll have is x over n plus 3. So this gives us the limit as n approaches infinity of the absolute value of x over n plus 3. Okay. Now, here's the deal. When you're computing this limit, what is being approaching to infinity, n or x? N. The x is irrelevant. So what I can do is pull out the absolute value of x, right? If I pull out the absolute value of x, then we have just the limit as n approaches infinity of 1 over n plus 3. Sorry, this doesn't need to be in absolute values anymore. But when you look at that limit, as n goes to infinity, what happens to 1 over n plus 3? What will that limit go to? That will go to 0. So what you'll have is the absolute value of x times 0. And if you multiply that, no matter what value of x you plug in, no matter what real number you plug in, your answer still is going to be 0. And what do I know about 0? When I compare it to 1, it's always less than 1. So this is true for all x. And because it's true for all x and we're dealing with the real number, your interval of convergence, right, in this example, that's right. The interval of convergence is basically r, the real numbers, is everything, which is equivalent to saying negative infinity to infinity. And that is your solution to this first example.